Hello students, welcome back. So today I am going to discuss Navy based classifier. So this concept is very important here. Here one highly practical Bayesian learning method is Navy based learner. So often it is also known as Navy based classifier. So it is one of the practical Bayesian learning method, that is Navy based classifier or Navy based learner. So, as you know, in some domains, its performance has been shown to be very compatible to the neural network and decision tree learning. So, in this section, as I introduce the Navy based classifier, and in the next section, as it applies to some practical problem of learning to classify the natural language text documents, right? So, first, let us see what is this Navy based classifier, then I will illustrate an example, right? Here, the Navy-based classifier it applies to learning task where each instance X is described by a conjunction of attribute values and where the target function that is f of x. So this can take on any value from some finite set capital V. Here, a set of training examples of the target function is provided and a new instance is presented which is described by the tuple of attribute values, that is a1, a2, an and so on up to am or an. Here, the learner is asked to predict the target value or classification for this new instance. So this is very important. So in Navy based classifier, the learner is asked to predict the target value or classification for this new instance. The Bayesian approach to classifying the new instances is to assign the most probable target value, that is a VMAP, given the target values A1, A2, A3 and so on up to AM. So that describe the instance, right? So here you can note down this particular formula. So this is nothing but the probable target value for the given attribute values, that is a1, a2 up to am, which will describe the instance, right? So it is given as vmap is equal to argmax p of vj bar a1 comma a2 comma a3 and so on up to an, where small vj belongs to capital V. Now we could attempt to estimate two terms in this particular equation based on the training data, right? So here we can also use the Bayes theorem to rewrite this expression as, means here we are using Bayes theorem to rewrite this above equation or above expression as vmap equal to argmax p of a1 comma a2 comma a3 and so on an bar vj into p of vj whole divided by p of a1 comma a2 comma a3 and so on up to an, where small vj belongs to capital V. This in turn simplified as argmax p of a1 comma a2 comma a3 and so on an bar vj into p of vj, where vj belongs to capital V. So now we could attempt to estimate the two terms in this particular equation based on the training data. Here it is easy to estimate each of the P of Vj simply by counting the frequency with which each target value Vj it occurs in the training data. However, estimating the different P of A1, A2, A3 and so on An bar Vj terms in this fashion is not feasible unless we have a very large set of data. The problem is that the number of these terms is equal to the number of possible instances times the number of possible target values. Therefore, we need to see every instance in the instance space many times in order to obtain the reliable estimates. The Navy based classifier is based on simplifying the assumption that the attribute values are coordinately dependent given the target value. So, in other words, the assumption is that given the target value of the instance, the probability of observing the conjunction, that is A1, A2, and so on up to An, is just the product of probabilities for the individual attributes, that is P of A1, A2, so An bar Vj is equal to pi I, that is pi I into, that is pi I P of Ai bar Vj. So substituting this in this particular equation, we have the approach used by the Navy based classifier. As our Navy based classifier is finally given as uh, Vnb is equal to argmax P of Vj into pi I P of Ai bar Vj, where Vj belongs to capital V. Here VNB denotes the target value output by the Navy based classifier. So you can notice that in a Navy based classifier, the number of distinct P of AI bar Vj terms that must be estimated from the training data is just the number of distinct attribute values times the number of target, that is the distinct target values, which is a much smaller number than if we were estimate the P of A1, A2 and so on An bar Vj terms as the first contemplated. So this is very important. Now take an example. So an illustrative example here. Let us apply the Navy based classifier to a concept learning problem that we considered during our discussion of decision tree learning. So the same example that I have taken here, that is classifying the days according to whether someone will play the tennis or not. So this particular table provides a set of 14 training examples. You can see there are 14 records. So these are nothing but training examples. So this table, it provides a set of 14 training examples of the target concept, that is play tennis, where each day is described by attributes outlook, temperature, humidity, wind, play tennis. Here we use the Navy based classifier and the training data from this table to classify uh, the following novel instance as outlook equal to sunny, temperature equal to cool, humidity equal to high, and wind equal to strong. Here our task is to predict the target value, that is yes or no, of the target concept play tennis for this new instance. Now instantiating the previous equation, right, to fit the current task. Here the target value, that is VNB, is given by VNB equal to argmax P of Vj into pi I P of Ai bar Vj, where Vj belongs to yes or no. So yes or no is the target value here, right? So which is in turn given as VNB equal to argmax P of Vj. Here I have written the instances, that is P of outlook equal to sunny bar Vj, P of temperature equal to cool bar Vj, P of humidity equal to high bar Vj, and P of wind equal to strong bar Vj, where Vj belongs to yes or no. So here we can notice that in the final expression that AI has been instantiated using the particular attribute values of the new instance. So to calculate V and B, we now require 10 probabilities that can be estimated from the training data. First, the probabilities of the different target values can easily be estimated based on their frequencies over 14 training examples. So P of plate n is equal to yes, and its probability value is 9 by 14, that is 0.64, and P of plate n is equal to no, and its probability is 5 by 14, and hence it is equal to 0.36. Similarly, we can estimate the conditional probabilities. For example, those for wind equal to strong. So the conditional probabilities are P of wind equal to strong bar plate n is equal to yes, which in turn given as 3 by 9 is equal to 0.33, and one more conditional probability is P of wind equal to strong. This is for no possibility, that is plate n is equal to no, 3 by 5 equal to 0.60. So using these probability estimates and similar estimates for the remaining attribute values, we can calculate V and B according to this particular equation, means according to this equation, right? So which is given as P of S into P of sunny bar S into P of cool bar S into P of high bar S into P of strong bar S is equal to 0.0053, and one more possibility is P of no into P of sunny bar no into P of cool bar no into P of high bar no into P of strong bar no is equal to 0.0206. Hence, the Navy based classifier assigns the target value, that is plate n is equal to no, to this new instance based on the probability estimates learned from the training data. Furthermore, by normalizing the above quantities to 1, we can calculate the conditional probability that the target value is no. So given the observed attribute values for the current example, so this probability is 0.0206 divided by 0.0206 plus 0.0053, so which the result come around 0.795. So this is the probability as per the given formula for the current example. Next is estimating probabilities. So up to this point, we have estimated the probabilities by the fraction of times the event is observed to occur over the total number of opportunities. For example, in the above case that we have estimated P of wind equal to strong bar plate n is equal to no by the fraction, that is NC by N, where N equal to pi is the total number of training examples for which plate n is equal to no, and NC equal to 3 is the number of those for which wind equal to strong. While this observed fraction provides a good estimate of probability in many cases, so it provides the poor estimates when NC is very small. So to see the difficulty that we have a sample containing only 5 examples for which plate n is equal to no, then the most probable value for NC is 0. So this raises two difficulties. So the first one is NC by N produces, that is NC by N, it produces a biased underestimate of the probability, and second difficulty is that when this probability estimate is 0, so this probability term will dominate the base classifier if the future query contains wind equal to strong. The reason is that the quantity which is calculated in the previous equation, it requires multiplying all the other probability terms by the 0 value. To avoid this difficulty, we can adopt a Bayesian approach to estimating the probability using the M estimate defined uh, as below. It is defined as follows, that is M estimate probability defined as NC plus MP divided by N plus M. Here NC and N are defined So in this equation, nc and n that are defined as before, and p is our prior estimate of the probability we wish to determine, and m is the constant which is known as equivalent sample size, which determines how heavily to weight p, which is relative to the observed data. Here, a typical method for choosing p in the options of other information is to assume uniform priors. That is, if an attribute has k possible values, then we set p equal to 1 by k. So, for example, in estimating a p of wind equal to strong bar plate tennis equal to no, we note that the attribute wind has two possible values. So, uniform priors would correspond to choosing p equal to 0.5, and note that if m is 0, then m estimate is equivalent to the simple fraction, that is nc by n. If both n and m are non-zero, then observed fraction, that is nc by n, and the prior p will be combined according to the weight m. The reason m is called the equivalent sample size is the previous equation, so that can be interpreted as argument the n actual observation by the additional m virtual sample distribution, that is m virtual sample which are distributed according to p. So this is all about the navy base classifier, right? I hope the concepts are clear. So in the next class that I am going to discuss base belief networks.